Well, welcome back. We are going to do part 5 of electrochemistry, and today we will be focusing on commercial batteries and corrosion. Now, we're not going to go into much depth in the area. We're just going to mainly accent, for a few select cases, the difference between the laboratory cells that we've talked about. In other words, making essentially a basic battery in beakers and just labware, and what is actually done commercially. Okay. And like I said, we're going to be doing corrosion as well. Just touch on that. Now, when we talk about batteries, what we are really talking about, as opposed to cells, is a system that is self-contained. And you're familiar with these. Any kind of ion battery, like lithium-ion battery that's in your cell phone or computer, or an alkaline battery that's in heaven knows how many devices that we use. It is portable, easy to use. We don't have the sloppiness of the beakers and having to make solutions in our own salt bridge, okay? So it is more of a commercial and generally utilizable item. And you probably are aware that there are two types of batteries, what we call a primary battery and then a secondary battery. And you've used both, I'm sure, many times. A primary battery is one that you do not recharge. When it dies, you don't even try to recharge it. You just pitch it to trash or recycle bin, and it's out of there. Secondary batteries, well, they're usually more expensive to buy. Chemistry's a little different. It's actually built to be reversible, so when it dies, you can recharge it. And we will, like I said, talk about examples there too. Now, in your textbook, they cover more examples than we are going to talk about. And you feel free to read and get whatever information you want in addition to this. But I just want to point out some subtleties that we don't realize whenever we look at a battery. Now, first one is the alkaline battery. This would be your AAA, AA, A through D batteries. And you've all seen these. Now, whenever we've done balancing equations early on, we had a zinc and, no, actually that was an iodine, but zinc and manganese system. And turns out that is a very nice, simple system. This is the cutaway of an inside of the battery. Now, for this system, probably no surprise to anyone, the anode is the zinc. Gives up electrons, why not? And what happens is it donates 2 electrons, and then we have 2 hydroxides, which will interact with the zinc, and that ultimately goes to zinc dioxide, which then loses water, and you form zinc oxide, okay? Now, if you'll notice, for efficiency, our zinc anode actually doubles as the can that holds the battery. So depending on how much zinc is in here and the form it's in, that will contribute to how much current you get out, and it will contribute to how long the battery is useful its life. Now, on the other side, the cathode, we have manganese dioxide. Notice that is going from a +4, interacts with water, and it accepts the electrons to form manganese +2. Lose 2 up here at the anode, gain 2 down here at the cathode. Now, the waters, if you look at this, this is pretty slick, I think. The 2 waters will react with that manganese or the oxygen that comes off, and it gives us two hydroxides, which of course can go back up here and be used with the zinc, and it forms a dihydroxide, a manganese dihydroxide. So if we look at how this works, we have electrons coming off the zinc. They will come out the bottom of the battery. That's the one with a little inset dimple, okay? You have the little button on top and the little dimple on the other side. So your electrons come out of here, go wherever they go, and come back. Now, here, this is a cheap battery, so you don't want to meddle if you can get away with it. So carbon electrodes work, and they work well. Now, if you'll notice, we have hydroxide and water for the anode that we need to have in some proximity. And we have water and hydroxide for the manganese part. Same thing, just one is they're being used for different purposes. Well, similar purposes, not the same. Now, in order to have these two species available to both, we have a paste in the middle here, and that paste will have the goodies in it, okay? And we're talking by goodies here, since the electrode, the cathode, is the carbon we talked about, this manganese dioxide is in the paste, but it does not go over as far as the zinc, and we have the hydroxide. And in with that, we will form a little bit of water, okay? Notice it forms here and it's used here. Now, they probably put a little bit in to start with. Now, like I said, the size of the battery makes a difference on the current it can handle. The larger the battery, the larger the current, and depending on the load. So if it's the same load, same application, and you're using the same amount of current, then the larger battery will also last longer for that reason. It can supply it longer. What will not change with respect to the size of the battery, if you have the same ratio of anode and cathode materials, is your voltage will be the same, right? Remember, we talked about standard voltage and then changing it using the Nernst equation. So the 1.5 volts, it's adjusted to that. And as long as that ratio of reactant to product does not change, we're good. Now, we don't need to go any deeper into the chemistry. This is the basic chemistry. But your batteries that you buy commercially have more additives inside to add to the battery stability, make sure that the chemicals such as the manganese dioxide do not clump up and become less reactive. There's a lot of things that are going on behind this main scene here. And as a result of these changes and improvements over the years, from about the 1960s to early 70s, if you took that battery life as one, and you took the same battery today, and I mean the same size of battery for the same application, it would last probably 2 or a little more than 2 times longer, even though it probably doesn't weigh anymore. And as I said, the size is the same. All commercial batteries are like that. They will have additives. There is engineering, special chemical and mechanical engineering that goes on to improve the system. Now, that's the only primary battery we're going to talk about. You are familiar with things like silver batteries, the little circular button batteries we use for watches and assorted other small applications. Mercury is used for that, or was used. It probably is not, at least in the US, it's not used anymore. Lithium batteries, you have two types. You have the lithium battery that's a primary battery, you throw it out essentially. And then you have the lithium ion battery, which can be, and it's designed to be recharged. We'll talk about that. Now, let's move on. Oh, I don't know where this came out of. I don't think it's your textbook. But the dry cell battery, like we just got done talking about, was invented more than 100 years ago. And the battery, note this, back then was a zinc inner case that acts as an anode and a carbon rod in contact with moist paste of solid manganese dioxide. Does that sound familiar? Sure should. Now notice it's an acid version, not a base version, and they use ammonium, or they used ammonium chloride as one of the components in the battery. So that basic idea has been around quite a while. Now, let's talk about secondary batteries. And we're going to talk about two. The lead acid battery, the auto battery, basically what starts our car, and then we'll touch on the lithium ion battery. Now, let's go over the chemistry first. You have, it's basically a lead battery, okay, lead based. So for the anode, what we have is lead metal reacting with the half acid sulfuric, and we form lead sulfate. The acid or the proton comes off, and we end up with 2 electrons. Now, on the cathode, what do we have? In this case, we start with lead dioxide, so that we have lead 0 for the anode, lead +4 for the cathode. The acid is used here. It reacts with the oxygen, or the oxide, I should say. And what we end up doing is using the 2 electrons generated here, and we form lead sulfate plus water. Now, notice this lead sulfate, we went from +4 to +2. And here we went from 0 to +2, but it's the same product. That is some pretty nice engineering. So you have a very simple and versatile system. So if we look at the overall reaction, we see that we have the lead cathode, the anode material, acid, and of course water. That's where the aqueous comes from. And then we end up with the same product for both, as we showed above, plus water. And each cell has, the, depending on the concentrations, is designed for, and these are solids, about 2.1 volts, okay? So how does this work? Well, on the discharging cycle, you go in and you start your car, and it will draw a large current, a lot of electrons flow. And with the voltage of the battery, we'll show you another slide with a little more information. That will start your car. Now, you need a lot of power because you have that engine, and you are turning that engine over, and all the metal parts in the engine, all the cylinders are moving, other stuff is moving in the car. So it's not an easy job. Needs a lot of horsepower. Now, once your car is started, the battery is not needed anymore, because we have what's called an alternator on the car, or a generator, depending on how old the car is. But anyway, what will happen is that electrical energy that's generated by the engine, okay, that is used for 2 purposes. One is to run the engine. That's what provides the electricity for the spark. That's what provides the electricity for your radio, for your headlights, everything else. It also is used for recharging the battery. So you have a small slipstream of that electricity. And it converts the lead sulfate back into, reacts with the water, and it goes back to the starting materials, the cathode material, the anode material, and the initial sulfuric acid. Pretty nice system. Okay, now you've probably seen, maybe you have lifted an auto battery. They're pretty good sized, okay? And they're heavy. Why is that? Well, we'll get to that in just a minute, but let's look at what the inside of a battery looks like. Let me blow this up just a little bit. Okay, you probably remember at the top of your cells or your battery, you have two posts that come out. One will be red and one will be black. And one obviously then is negative. Electrons come out of there. The positive ones accept the electrons. Now, down here, what we have are plates. Okay, these are heavy plates, and they are made out of lead. Now, these light blue colored ones on the end are the anode. In other words, it is lead metal. Now, because the metal's coming off and going back on, do you think it looks like lead? Do you remember what we talked about with the copper and some other metals? It will look more like a black coating. Okay, remember we talked about metal blacks, just touched on them? So we have a series of panels that, or they call them grids as well, that would be lead metal. And then in between, what we have are panels or grids that are filled or contain lead dioxide. So each pair of these grids, one and one, would be a cell. This would be like our two beakers, and we would have lead on one side, lead oxide on the other, okay? Or lead dioxide, okay? Now, with that in mind, let's answer some questions. Okay. There we go. So the first question is, well, if the cell only generates, a single cell generates 2.1 volts, then how do we get 12 volts out of a car battery? You may be aware that they generate 12 volts. Well, the way we do that is we put them in series. So if you have 6 batteries in series, the voltage builds and you end up generating about 12 volts. If you'll remember, in some devices, whenever you replace batteries, if you have 2 pen-light batteries, sometimes you will take them and you'll put them in series. In other words, you will put one positive to the other negative. So the current and the electrons, I should say, flow through both batteries, so the voltage is essentially double. Same number of electrons, but you double the voltage, okay? So that is how we get 12 volts. It would be like 6 pen-light batteries lined up, except these are much bigger. Now remember I said that we use high current. Now the current that's used is about 500 amps. Now when you think about it, you can die from less than 1 amp of current, depending on the voltage. But 1 amp of current can do a lot of damage. Okay, so 500, probably don't want to get that shorted through your system. Okay, why the current? Well, power, like we talk about watts, 100-watt bulb, power is equal to voltage times current. So to get the power that you need to start the car, you have the 2.1 volts, and it turns out it needs to be that 400 to 500 amps, and you will see batteries with ratings of up to 600 amps that you could buy off the shelf. Okay, now battery life. Turns out, fortunately, I mean, they're expensive batteries in a way. You can spend $150 easily for a battery. The battery life is usually around 4 to 7 years. And part of what makes a difference on battery life is what you're using it for. If you are stressing the battery, in other words, pulling high currents for fairly long periods of time, say your car is difficult to start, that will be an issue. And your battery probably won't last as long as if it just takes one little, click and it's off and running, okay? Now, turns out we need to be careful, and when we design these batteries, we need to be careful of both high temperature and low temperature situations. High temperature would be if you live in the Gobi Desert and it gets to be 120 every day. What happens is the battery, because of the high temperature and the reactions in a battery, what happens to the kinetics in anything as you increase temperature? The rate of whatever it is, the kinetics increases, right? So if there are little drains on the battery, little shorts that wouldn't make any difference if the temperature was low, at high temperature, the drain would be higher. Meaning, if you had a car and you parked it in the sun in one of those high temperature areas, you could come back in 2 weeks and the battery may be dead. If it's a low temperature area, that should not occur. Hold on, just a second. So temperature is an important situation. If you live in a high temperature area, Arizona, what you may want to do is buy a battery that's designed more specifically for high temperature applications. And then we have the low temperature problem. And that's one that most of us suffer with more. What will happen in a fresh battery, you can go out, it doesn't matter if it's, if there's frost on the car or not, but you can hit the starter and it will start right up. Unfortunately, with low temperatures, it slows all the chemical reactions, just the opposite, obviously, of high temperature. So, as the temperature gets lower, the kinetics in the battery slow, and it means it will become more difficult to start. So, if any of you ever been in a situation where you go out in the morning and you go to start the car and it just kind of growls a little bit, takes a little bit longer to start, it's just not right. And then when you go out at noon or in the afternoon after work and you go to start the car, it starts right up and you say, oh, not a problem. Actually, it probably is telling you, hey, I'm about to have a real major problem and I'm going to stick you somewhere. So if at lower temperatures your battery starts misbehaving, slow to start, you go out, you turn on the car, does start, and your preset radio stations are lost, that's also an indication that you are close to needing a new battery. Now, lastly, safety. This has water in the system, right? What we discussed here. It was water related to the sulfuric acid. Well, it turns out with the cycle of starting and recharging, especially the recharging, what happens is a little bit of the water decomposes, and it decomposes into oxygen and hydrogen gas. Now, the oxygen really isn't a problem in a way, since there's enough of it in the air. The problem is the hydrogen. Whenever you have hydrogen, it can build up in the system here within the case. And whenever you go to like maybe jump start the car, the battery's not behaving well, so you jump start it, and if there's a spark and hydrogen available, the batteries can blow up. Now, that is due to something called overvoltage. We will not talk about it here. In the next section we do on electrolytic cells, we will talk about that. And it will also explain to us why, for something like this, we can recharge a battery, because under normal conditions, we can take care of this, okay? Some exceptional conditions we can't. Whereas for the alkaline battery, if you remember, we showed you that there was water involved in that, okay? Okay, there's water involved. Now, that's why you don't redo or recycle these batteries, recycle with respect to recharge, because of that water will break down as well. It will form hydrogen and oxygen. These are sealed containers. The containers will split and you'll get this goo, the basic goo, the paste, in your electronic device, and it could ruin it. Okay, but we'll talk about that a little more the next time. Okay, just some numbers there. I don't think we need to go over those. Now let's talk about the secondary battery of the lithium ion type, okay? Now, this is something similar to what you would have in your computer now, or smartphone. Now, let me say up front, what we are going to present is a general approach to lithium ion batteries. Each manufacturer will change some of the components here, as well as have other additives to improve the safety and performance, okay, of the system. Now, what the anode is here, it's a lithium mixture with carbon. Now, this C6 is supposed to represent a graphite type carbon. Now, if you'll remember, we mentioned in one of the other lectures about taking a pencil, and when you write, that lead or graphite in there. Lead is for a pencil is actually just a carbon rod. What happens is these carbon or graphite sheets smear out, and as they smear out, that's what leaves the black mark on the paper. So if you could go down to the nano scale and separate those graphite sheets, what you could do is lay lithium ions in between. So it would be like filling in a cake. You have a sheet of graphite. You have a lot of little dots of lithium. Then you have another sheet. Then you put more dots of lithium, and another and another and another. Now, the purpose of that is to keep the lithium metal from clumping and to make it more available. And by available, I mean so that it can drift out, diffuse out of this material, the anode material, and then be reloaded back in when the ion is reduced. So, for the anode, what happens is this material, this layered material, will lose an electron. The lithium will diffuse out and go toward the cathode. So we have the lithium going one way and the electron going another way to do what we want it to do. And that will leave us with the graphite with no lithium in it at all if it's completely depleted. Now, at the cathode, what happens? Well, we have this mixture. It would be lithium 1 minus X, and I'll get to that in a minute, with manganese 2 tetroxide. Okay, now this means this lithium tetroxide, or this lithium, what that will do is neutralize the charge on this particular species. And if we look at what it would take to neutralize this, we have -8 for the oxygen and +8 in theory for the manganese, meaning 2 manganese +4, but they're not always all +4. There's a little bit of +3. So if there's a manganese +4 and a manganese +3, that's +7, right? So we need another plus charge to neutralize the 4 oxides. That's where this comes in. This is proportional to how much extra manganese +3 there is, because it does not neutralize the oxygen. Okay, so what happens here is, as this material, this is the cathode material, it will accept an electron and it will go to a mixture of manganese +4 and manganese +3. So you're forming more +3. That's where this electron goes. So there's less +3 here, there's more +3 here, so it is being reduced. And since it's being reduced, we need more lithium, and that's where this extra lithium here goes. That replaces, or moves in to fill this void, okay? A little bit confusing. If you think about it, do a balancing of equations mentally. Just keep track of the charges and you'll see what's happening, okay? So overall, we have the anode with the graphite. We have the cathode with the partial lithiated manganese oxide. And what we end up with is a manganese +3, manganese +4 material plus graphite. And that voltage for the batteries, the way they're constructed, is about 3.7. Now, there are different manufacturers, and all of them are going to be right in that range because they're all vying for the same applications. Okay? Now, one of the things, because of these batteries, they do have quite a bit of energy. And because of the components that are in there and the construction, they are susceptible to fires depending on construction. So if you have something that does not separate materials, or something that's flammable, if the wrong things touch, it would be like a short, where you have the anode and cathode in direct contact, where those electrons, instead of going around the way we want, they can go directly from the anode to the cathode. That will generate a horrendous amount of heat, and that will lead to a fire. If you have a case that leaks, again, if air gets in, and this lithium, which is very reactive, will react with the air, it again will generate a lot of heat and can lead to a fire. Okay, let's see here. Let me decrease that size a little bit, and if you have any desire, you can get a picture of that and read it over, but it's pretty much just what we talked about already. Okay, now last topic, corrosion. Now this is a huge topic. We are not going to spend a lot of time on it. We have other stuff to do, but I want you to be aware of it. Corrosion is a huge problem. But before we talk about how big it is, let's talk about what corrosion is. Now, this is a very simple example illustrating what would happen if we had something like iron nails, cheap nails, not steel or stainless steel, but just iron nails, and they were left outside in the elements. Now, it turns out this is like a battery. We have iron, solid, oxygen, obviously from the air, and I put sodium chloride here, but it could be any salts, and salts are readily available in the environment, as are water, or as is water. And that will lead to rust. Fe2O3 is generally rust. Okay, so we look at this, and from the battery perspective, iron is going to a cation, right? So that means that is our anode. Oxygen elemental is going to oxide, so that is our cathode. The salt is our electrolyte, and water is our solvent. So we have all the components of a battery. Now, this is actually just shorted out, right? We don't actually have the iron and the oxygen separated so we can use the electrons. But nonetheless, you can see there is a parallel to what we've just been talking about. Now, let's talk about the magnitude of corrosion problems. Now, corrosion problems, we normally think mainly of iron or simple things, but it could be any metal at all, any alloy, they would contribute. Now, the information I have here is probably 4 to 5 years old. So this US alone number is probably considerably smaller than it actually is today. And back when this number was reported, about $437 billion a year in corrosion losses. So if you live somewhere where there's salt in the roads, your automobile corrodes. We've heard of bridge corrosion and how many bridges are in bad shape and need replacing. Horrendous problem, okay? Now, if we look at the weather as an example of how things can vary, if we take a car on the East Coast where there is snow and ice and salt, and or the Midwest versus California, where at least in our area, we don't have any of those problems unless you spend a lot of time on the beach. Then you will maybe see some impact. But on the East Coast, not necessarily, not so much now, but in past years, if you bought a new car, literally within 3 to 4 years, you would see the car rusting out. Toward the bottom, on the paint, you would see blistering. And if you scratch those blisters, you would see the paint would come off, and you would see the rust underneath, that orangish brown color of rust. And it would get so bad that within 5 or 6 years, in very heavily salted areas, that your floorboard where you put your feet in the back seat or the front seat, they would rust out to the only thing keeping your feet off the road might be carpet, okay? And that's also bad because if you have a leaky exhaust systems, which were more common then than now, you would get carbon dioxide, carbon monoxide up into the automobile, and obviously that's not a good thing. Not that long ago, some of you may actually remember the Statue of Liberty was restored. Now, that's copper corrosion. What had happened was the rains and just, acid rain, pollution would get on that copper. Now, copper is not as corrosive or not as easy to corrode as iron, but nonetheless, under the right environment, it will corrode. And it cost about $277 million to redo the parts of the Statue of Liberty that were in bad shape. One of my favorite applications is in pipelines. We used to live in Texas, and one of the things they would do is put something called a pig into a pipeline. So if you had a natural gas pipeline or an oil pipeline, you would put something that looked like a huge beach ball in, very thick. But the trick with this beach ball is it would block the flow. So if you pushed oil or gas through, it would push this beach ball through. And inside the beach ball, there was an array of electronic devices that would detect how there was a magnetic field generated, and it would detect how that magnetic field interacted with the pipe. So let's say you had you were measuring the sensitivity or the response on the inside of the pipe, and you said, okay, most of this is okay, but there's this spot, the magnetic field is too weak. Well, that would be an indication something was wrong. Maybe you had a leak or it was getting close to leaking. So what you would do is map that out electronically. You'd have your pig going down the line. You would have a truck or some device, or maybe even an airplane flying over and a recording. So if you said, aha, here's a problem in this section here, what you could do is go back and have inspectors look at it and find the problem. Now, what happens if you didn't do that? Well, obviously you would have a leak. And obviously that's not good for the environment. Now, a gas leak is one thing, it doesn't make the mess. I'm not saying it's not going to do environmental damage because you don't want the gas out, but it's not the same as oil that can ruin the soil. In Alaska, they used a smart pig. Now, that pipeline is about 800 miles long, and it's a ½ inch thick, and I think about 10 feet to 12 feet in diameter. I won't swear to that, but it's big. Now, can you imagine up there if you had an oil leak and you couldn't find it or didn't find it for weeks or months? That would really make a mess. So they have a huge smart pig there that will do the same thing up there. Now, to finish off corrosion, as I said, we don't want to get into it in any depth. One of my favorite applications or inhibitor applications is an aluminum soda can. We've seen aluminum cans, we've used them for years. Well, it turns out if you took an aluminum soda can and did not protect it for corrosion, if you had any kind of soft drink like Coke, Pepsi, anything with phosphoric acid in it, and CO2 and salts don't help, it turns out that can or that aluminum would corrode in about 3 days with the amount of phosphoric acid present. Now, have you ever had a 6-pack or a 12-pack or a case of soda and you had leaky cans? I never have. I have had cans where somebody, had maybe accidentally poked a knife or something into them when they were opening a crate or a container, but that's all. So why don't they corrode? What did they do to protect that? Well, it turns out if you look at the inside, the can does not look silvery. It has more of a light yellow to maybe slightly goldish tint. And what that is, it's a very thin layer of epoxide coating. You know how you have like deck stains in that are epoxides, and they have like a light yellow coating? That's what is used. Probably not the same one we put on our deck, but it protects the can. And at this point, now this again is 5-year-old information, the estimate is that to corrosion now, there is a 0.002% failure rate in cans. And that comes out to about 1 can in 50,000 cans. I'm impressed. I really am. Okay, that is the end of this particular part. As I said, it was more applied. I want you to be aware of the concepts, but there's no calculations or anything. I'm not going to ask you tricky questions on this. You know, knowing a primary from a secondary battery, what they are, and knowing what corrosion is, I think is that's about where we want to be. So it's basically some practical information you may be able to use sometimes. Now, next time we meet, we are going to talk about electrolytic cells. That is the opposite of a battery. That you could think of that as the recharging half of the battery. You are taking electricity from another source and regenerating whatever it is that we use for a battery, or we are doing a chemical reaction to intentionally make something. Okay, so it's a synthetic method, and we'll touch on applications, and then there's a couple calculations we'll talk about. Up above, where we talked about voltage, all our calculations were aimed at what is the voltage of the cell? How can we control it? Down here at the end, we're going to look at current, basically, and say, if we have this current, in other words, number of electrons, how much of a material can we make? How much can we use? So these calculations will accent current. Okay? All right, that is it. Thank you.